Now, we are talking more about muscle physiology today. Are y'all ready? Okay, so before we jump into some new stuff, let's review what we talked about last time, yesterday, right? It wasn't that long ago. Okay, so the first part of our muscle contraction happens right here at the neuromuscular junction. What happens first? An action potential moves down the axon. When it gets to the synaptic terminal, it's going to cause what to open? The voltage-gated calcium channels. Calcium is going to go which direction? Into that axon terminus. When it comes inside, what does it cause to happen next? Little acetylcholine packages, ACH, those vesicles, exocytose, they leave the axon terminus, they pass through the synaptic cleft, and they bind to what? Acetylcholine receptors, which are also ligand-gated channels. And so they open up and they allow what to come into the muscle fiber? Sodium comes in, potassium goes out. And then that flips the polarity of the membrane. So now instead of the inside being negative, now the inside is more positive. Okay? And we have an end plate potential. We have a buildup of positive charge right here at the end plate. Okay? That was step one. And then we watched a pretty video. And then we moved on to step two. Okay, let's see if you remember what happened in step two. And we got our end plate potential, positive inside, negative outside. And then we're going to start an action potential, a wave of depolarization, because we will open voltage-gated sodium channels. When we open those voltage-gated sodium channels, sodium will come in and make the inside more positive, and that will cause more sodium-gated or voltage-gated sodium channels, more of those to open, which allows more sodium to come in, which causes another sodium channel to open, which causes another sodium channel to open, and we spread this positive charge throughout the muscle fiber. Okay? Then we also said to repolarize, to bring it back to negative inside, positive outside, we have to open another channel, our potassium channels. So those will open up and allow potassium to go out, which will bring us back to close to our resting membrane potential. Negative inside, positive outside. Right? Okay. So that's where we've gotten so far. We're starting an action potential. We've got a change in charges inside of that muscle fiber. Now, our next step, step number 3, is called excitation contraction coupling. Okay, so now we're going to take that excitation that we've done, so we've polarized or depolarized that muscle fiber, and we've excited it, and now we're going to couple that with our actual contraction of our muscle. So we're finally making it to where the muscle is actually going to move. Okay, we're getting there. It's exciting. Okay, so what we're going to use in this process are our T-tubules and our sarcoplasmic reticulum. So, do you guys remember what your T-tubule is? So here's a picture of him. Here's the T-tubule. What is he connected to? I have a big picture of him drawn over here. This picture. You remember it, but you don't know what it's a picture of? Okay, so remember it was that sarcolemma, the plasma membrane, that is bending in and going inside of the muscle fiber. So this T-tubule right here, that's now a big yellow clump, is connected to that plasma membrane. It's continuous with the plasma membrane. From our very last step that we just talked about, what is happening on that plasma membrane? An action potential. So the action potential is spreading because our sodium channels are opening up. And now because these T-tubules are there, that action potential is now going deep inside the muscle fiber. Cool? So on our picture here, you see this is our muscle fiber. This is our plasma membrane, our sarcolemma. And wrapped around our bundles of myofilaments are those T-tubules. So they're getting in there and they're getting close to those fibers. Okay. Now, do you remember what these blue guys are right here on either side of the T-tubules are? Yes. Sarcoplasmic reticulum, the SR. Okay? What do these guys make up? The sarcoplasmic reticulum and the T-tubules, they make up a triad, right? A triad. Okay? And right around that T-tubule, we have enlargement of the sarcoplasmic reticulum, the terminal cisternae. So they're these big enlargement of sarcoplasmic reticulum. Okay. What does the sarcoplasmic reticulum hold inside of it? It's a reservoir for calcium. Okay? So we've got a bunch of calcium stored up in the sarcoplasmic reticulum right beside these T-tubules that's connected to the plasma membrane where the action potential is going on. Okay? Now we're going to put pieces together. You ready? Okay. Here we go. We've got an action potential coming down through that T-tubule. It is going to cause voltage-gated calcium channels to open up on the sarcoplasmic reticulum. Right there by the T-tubule. Really exciting. Okay, so we've got these voltage-gated calcium channels that are on the sarcoplasmic reticulum. When they open up, there's a whole lot of calcium inside the sarcoplasmic reticulum, and so all that calcium is going to gush out into the cell. This is the stuff I love about biology, all these little processes. Okay, so now we have a muscle fiber that once did not have calcium in it, but it was all stored up in the sarcoplasmic reticulum. Now that the action potential has come through, calcium channels are open, and now that muscle fiber is full of calcium. Okay, now what's that calcium going to do? Let's see. I can erase some of my mess. Okay, so we've got to go back to the structure of our thin filaments and our thin filaments. Yes. Okay, I'll try to slow down. So, we have to go back to the anatomy of our thin filaments. Okay? What makes up thin filaments? Actin is one part. Okay, so it's hard to see on this picture because it's really small, but I'm trying to go slow, it's so hard. Okay, the actin are the little blue circles in the picture, okay, that form the beads on the screen. Okay, then what's the name of the protein that covers the myosin binding site on the actin? Tropomyosin. Okay, so tropomyosin is wrapped around. And then what's the name of the protein that holds the tropomyosin in place? Troponin. Okay, so troponin holds the tropomyosin and covers up those binding sites. Okay, you ready? When troponin is knocked down the calcium. It holds the tropomyosin over those myosin binding sites. When calcium binds to troponin, it causes a change in the shape and moves the tropomyosin out of the myosin binding site. Yes. Okay. So I'm gonna write it out. Okay. So calcium is going to bind to troponin. Where did that calcium come from? Sarcoplasmic reticulum. Okay. What opened up on the sarcoplasmic reticulum? Voltage-gated calcium channels. Why did they open? Yes, because the action potential got there. Okay, all from that neuron originally. Okay, so the calcium binds to troponin. Troponin changes shape. Okay, that change in shape moves tropomyosin. When the tropomyosin moves, it exposes myosin binding sites on the axon. I guess it's got one more. Okay. So now that the myosin binding sites are open, the myosin can grab onto the actin and move it. And we're going to get a muscle contraction. Exciting, right? Okay. So we're starting at the very beginning. Okay. Start at the very beginning. Okay. So what is sent down the axon? Action potential. When it gets to the axon terminus, it opens what? Calcium channel. Calcium is going to move into the axon terminus, and it causes the release of, well, the calcium moves into the cell, and then the calcium causes what to be released from the axon terminus? Acetylcholine. Okay? Acetylcholine goes past the synapse and binds to a receptor, acetylcholine receptor. Okay, that acetylcholine receptor allows sodium to move into the muscle fiber, potassium to move out, which causes that a depolarization. We end up with a positive inside and negative outside, and we get an end plate potential, a little action potential at the very end. Okay? That then causes voltage-gated channels, sodium channels to open on the sarcolemma, which allows sodium to come into the cell. Okay? That sodium that comes into the cell depolarizes it, makes it positive inside, negative outside, and now we have an action potential there on the muscle fiber itself. That action potential travels through the T-tubules, and right beside the T-tubules are the terminal cisternae of the sarcoplasmic reticulum, big sacs of the SR. On the SR are voltage-gated calcium channels. When the action potential gets there, what opens? Calcium channels. And the calcium leaves the sarcoplasmic reticulum and floods the muscle fiber. Okay? That calcium then binds to troponin, which changes shape and moves the tropomyosin out of the way. And now, on our actin, we have myosin binding sites that are available. So cool. And what gets me about this is happening all the time. Right now. This is happening in your body all over the place. And you don't even have to think about it. You have calcium channels opening, you got sodium channels opening, you have potassium channels opening, and it's all working. And before today, you didn't even know it was happening. Crazy. Yes. So it is a great question. So you just get people who are curious over the years, and then they learn a little bit of the picture. So they may learn from looking at the cell that muscle contraction happens when there's a lot of calcium in the cell. But muscle contraction doesn't happen when there's not calcium in the cell. What's making that change? And then they said, oh, here's a channel that lets calcium into the cell. How does it work? It requires a voltage change. And so it's just taking little discoveries, little by little, and putting them together to make a big picture. Yeah, crazy stuff. All right. Yeah. It's happening because it all gets a signal from the axon. So it has to be your brain or your spinal cord that is starting this whole process. And we're talking about skeletal muscles, right? So they're voluntary. We're choosing to do this, whether consciously or subconsciously. We are deciding to make this happen. So when you're saying move your arm, what you're really saying is send an action potential down to my muscle fibers and start this process of happening. Okay, you guys want to watch a video? Wow. Okay. I'm going to pretend that y'all don't like watching videos more than you like watching me run around the room.
Conducts action potentials that travel through hundreds of skeletal muscle fibers within a muscle. The sequence of events that converts action potentials in a muscle fiber to a contraction is known as excitation-contraction coupling. If we look at a single muscle fiber, we see that an action potential travels across the entire sarcolemma and is rapidly conducted into the interior of the muscle fiber by structures called transverse tubules. Transverse, or T-tubules, are regularly spaced enfoldings of the sarcolemma that branch extensively throughout the muscle fiber. At numerous junctions, the T-tubules make contact with a calcium-storing membranous network known as a sarcoplasmic reticulum, or SR. Where it abuts the T-tubule, the SR forms satellite bulges called terminal cisternae. One portion of a T-tubule plus two adjacent terminal cisternae is known as a triad. The membranes of the T-tubule and terminal cisternae are linked by a series of proteins that control calcium release. As an action potential travels down the T-tubule, it causes a voltage-sensitive protein to change shape. This shape change opens a calcium release channel in the SR, allowing calcium ions to flood the sarcoplasm. This rapid influx of calcium triggers a contraction of the skeletal muscle fiber. Thus, calcium ions are responsible for the coupling of excitation to the contraction of skeletal muscle fibers.
Okay, how are we doing so far? Okay, you ready for the next step? Why not, right? Okay. All right. It says that you'll be familiar with this from this week's lab, but it's okay. You will now know it before this week. It'll be great. Okay. So now we have to talk about how we actually get movement between the actin and myosin. Okay? So remember our structures. We've got the actin actin with the myosin binding sites. And our myosin, so there's your actin with the little dots on them. Calcium is bound to troponin with the tropomyosin. Okay? And then myosin has, we showed you a picture earlier, he looks kind of like a golf club. He looks like that. You've got a head and a tail. And the head can move. Okay? So we're going to look at how this actually happens. How does that myosin grab onto the actin and cause them to slide? Okay? And remember, when that happens, when you get sliding, that is when your muscle will get shorter and you'll have a contraction. Okay? So this is a muscle contraction right here. Okay, just zoomed in really, really close. All right, this process requires energy, and the energy we're going to use is in the form of ATP. Because we have to have ATP in order for this process to happen. And this cycle will continue as long as there is ATP, as long as there's energy, and as long as the calcium is bound to troponin. Because as soon as that calcium leaves, the troponin goes back to the original shape, and he moves that tropomyosin over top of the actin, over top of those myosin bodies, and closes the whole thing down. Okay? All right. So, one thing, I'm going to write it over here on the side of the screen, that we need to remember that will make this process make more sense is when myosin is bound to ATP, so myosin plus ATP, he will not stick to actin. Okay, so when myosin is bound to ATP, he will not stick to actin. Okay, so just write you a little note of that, put it in your brain, and if myosin, or if actin, if myosin is ever bound to ATP, he will release his grasp from actin. And he doesn't want to bind both of them at the same time. Okay. Y'all ready? Here we go. Okay, in our first picture, we say that a cross bridge has formed. This is cross bridge formation. Cross bridge just means the actin and myosin are bound together. Okay? So actin and myosin bind together. At this point, the myosin is bound to ADP and phosphate. Okay, so at this point, it's bound to ADP and phosphate. And it's just sitting there stuck together. What do you think this used to be? ATP. Because remember, if you take these two things and stick them together, you get ATP. Okay? But we have them apart. We have both an ADP and a phosphate bound to myosin, and so now he's stuck to the actin. Okay, so they're stuck together. The next step we need to do is to do something to cause this head of the myosin to bend, so that as he's bound to actin, he can bend and move him and fly him. Okay? So we need to change something to cause that myosin head to bend. So what we're going to do is release the ADP and the phosphate. Okay? So the second step is the ADP and phosphate leave. Okay? When the ADP and phosphate leave, the myosin head bends. This is called the power stroke. Okay? And it's written there small underneath the picture. So when ADP and phosphate leave, myosin head bends, and you get a power stroke. Okay, now that's lovely. Now we still have myosin bound to actin, and he's bent as far as he can go. What are we going to do next? Okay, so our next step is going to be to add ATP. Now, what do you know about ATP when it's bound to myosin? It doesn't stick to the actin anymore. Okay? So if we add ATP, get what our book calls cross-bridge detachment. So the myosin head comes off of the actin. Okay? But he's still in that bent state. Right? We're going to eventually make it back up to that first picture. What do you think is going to have to happen next to get from here to here? The ATP does what? The process is called, it hydrolyzes. So the ATP splits into ADP and phosphate. Okay? So the ATP is going to split into the ADP and phosphate, and that's going to cause that myosin head to come back up to its normal place. And once it's back up to its normal place, it's going to then bind to the actin again. Then it releases ADP and phosphate, and it will bend and move the actin. Then it binds to ATP and releases. The ATP is hydrolyzed to ADP and phosphate. It straightens back out. It binds to the actin. You release ADP and phosphate, and it bends again. Then you bind to ATP, and it releases. You hydrolyze ATP, it straightens, and this process will keep going and going and going as long as there's ATP and as long as there's calcium. Yay! Okay. Here's a little video to kind of show you what's going on. So the red at the top is the myosin head. The green circle is ATP. Now it's ADP and phosphate. Those release and it moves. Okay, and so this happens and it causes that actin to slide and slide and slide. It makes the muscle smaller and smaller. I think, yes, I have a video next. Do you guys have any questions before we watch the video? So the actin and myosin are always there. Remember, I'm going to go back. I'm going to go back and we're going to look at the picture. Remember when we were talking just about the anatomy of a muscle fiber? And we said, this guy right here. So our thick bands and thin bands that are in our muscle fiber are just long pieces of these actin and myosin filaments. So they're just always there. They're there. And as long as calcium is present, the myosin sits there and he just hangs out, and the actin he sits there. But as soon as calcium comes along and opens up the site, the myosin heads start binding and bending and releasing, and binding and bending and releasing, until you get a contraction. Okay. What other questions do you have? Yeah. During the process. So when you first add ATP, the myosin head will detach from the actin. Let's see if I can get back to where we were. And then we'll watch it. Okay. So right here where the ATP is added, the myosin head detaches. And then it hydrolyzes, bends back up straight, and it attaches. All right, what else? Yeah. So it takes all of these together, but where you're actually going to have sliding is when the ADP and phosphate are released. Because when the ADP and phosphate are released, the myosin head fits. So that's your power stroke step. Okay. All right, let's watch it, but then if you guys have questions after we watch it, we'll answer those too, okay? Here we go.
The contraction of the skeletal muscle generates the force necessary to move the skeleton. A contraction is triggered by a series of molecular events known as the cross-bridge cycle, In a skeletal muscle fiber, the functional unit of contraction is called the sarcomere. A sarcomere shortens when myosin heads and thick myofilaments form cross bridges with actin molecules and thin myofilaments. The formation of a cross bridge is initiated when calcium ions released from the sarcoplasmic reticulum bind to troponin. This binding causes troponin to change shape. Tropomyosin moves away from the myosin-binding sites on actin, allowing the myosin head to bind actin and form a cross bridge. Also note that the myosin head must be activated before a cross-bridge cycle can begin. This occurs when ATP binds to the myosin head and is hydrolyzed to ADP and inorganic phosphate. The energy liberated from the hydrolysis of ATP activates the myosin head, forcing it into the cocked position. A cross-bridge cycle may be divided into 4 steps. Step 1. Cross-bridge formation. The activated myosin head binds to actin, forming a cross-bridge. Inorganic phosphate is released, and the bond between myosin and actin becomes stronger. Step 2. The power stroke. ADP is released, and the activated myosin head pivots, sliding the thin myofilament toward the center of the sarcomere. Step 3. Cross-bridge detachment. When another ATP binds to the myosin head, the link between the myosin head and actin weakens, and the myosin head detaches. Step 4. Reactivation of the myosin head. ATP is hydrolyzed to ADP and inorganic phosphate. The energy released during hydrolysis reactivates the myosin head, returning it to the cocked position. As long as the binding sites on actin remain exposed, the cross-bridge cycle will repeat. And as the cycle repeats, the thin myofilaments are pulled toward each other and the sarcomere shortens. This shortening causes the whole muscle to contract. Cross-bridge cycling ends when calcium ions are actively transported back into the sarcoplasmic reticulum. Troponin returns to its original shape, allowing tropomyosin to glide over and cover the myosin-binding site on actin.
Cool stuff, right? Okay. Now what questions? Yeah. So for the muscle to relax, the myosin heads will pop off of the actin. Right? So what has to be bound to the myosin to allow it to get off of the actin? ATP. So we have to have ATP to have that process happen. The other thing that happens is that our muscles come in pairs. There's a flexor and an extender. So if I do this, this is flexing, this side is extending. And so to get this to straighten back out, I use this muscle. So right now, this one's contracting, these are relaxed. But when I'm ready to straighten back out, I'm going to pop my myosin heads off of the actin. Okay, so now we're ready to go. And now this muscle contracts, and we'll pull it apart. But the myosin heads are off, so you're not like. originally there is some ATP that's there in the cell ready to use. Once that is used, you jump over to the creatine phosphate, which will add the feed back to the ATP to make those ATP again. Then you can also use fermentation, ATP or KS. Yep. Yep. Right. So we're gonna get to that in a little bit. It's on here. But your muscle has contracted involuntarily, so you don't want it to contract, and it has contracted. So dehydration can cause that because you're looking at your ions have gotten messed up. You don't have the right amount of sodium. You don't have the right amount of potassium. You don't have the right amount of calcium. You don't have the right amount of magnesium. And so those things are getting messed up, and you send signals that don't really need to be met. Yeah, they're pulling tight stuff. Yep. Yes. Mhm. Mhm. So, are you talking about this yellow string right here? Okay, so when calcium is not present, so the muscle has not gotten a signal to contract, this yellow piece is going to sit on the actin over top of these myosin binding sites on the actin. So as long as that tropomyosin is sitting there, the myosin can't bind. But when calcium comes into the cell, because he's gotten the signal from the nervous system, it causes components which causes that tropomyosin to shift down to here. And then you've got those spots open where the myosin can bind. So. All right. What other questions? Okay. I know this is a lot. I know this is more intense stuff than what we talked about before. But I think if you sit down with it, if you look at the pictures, if you watch some of the videos again, it'll slowly start sinking in. But you do need to spend time with it, okay? Just listening to it in lecture probably isn't going to be enough for it to actually make its way into your brain, okay? So, videos from, like the lecture videos, recordings with my voice and your questions and things like that, those are posted on Brightspace. I also posted these videos individually on Brightspace as well. So you can go find them and watch those little short videos, okay? All right, we still have 10 minutes. Y'all ready? Yes. Okay, so we've got contraction, but as we kind of alluded to already, we don't want contraction to go on forever. We want to be able to relax, okay? So in order to get that signal to turn off, there's a couple steps that need to take place. So, relaxation of a muscle fiber. Step 16, signals will stop arriving from the motor neuron. So your brain is no longer telling that muscle to contract, okay? If your brain stops sending signals, the voltage gated calcium channels here on this axon terminus won't open. You won't get calcium in here. You won't release acetylcholine. Okay, so you're going to stop the release of acetylcholine. So that's number 17. Okay? Yes. Exactly. Exactly. Yeah. And we have control over this too, right? Because moving like this causes contraction, stop contraction, right? Think about writing and all the muscles involved in that process. And with, like you're turning out, okay, this muscle contract, this muscle contract, this muscle stop contracting. Your brain does all that. So, almost as if it was designed that way. Anyway, okay, so number 17 was we stopped the release of acetylcholine because we're no longer getting the signal to release acetylcholine, okay? Number 18, once we stop releasing acetylcholine, there's going to be a less acetylcholine there in that synapse, that little space. And so the acetylcholine that's bound to the receptors will dissociate. It will come off of the receptor because there is less in the area. So you're going to want to go to where there is less of you. Okay? So acetylcholine comes off of the receptor. Okay? Then, number 19. The free acetylcholine is eaten up by acetylcholinesterase. Okay? And so it gets rid of the acetylcholine that was in that synapse. And if there's no acetylcholine bound to its receptor, you are no longer letting sodium into the cell and passing it out. So you're no longer depolarizing the muscle, plasma membrane, the muscle sarcolemma, which means you're no longer opening the calcium channels off the sarcoplasmic reticulum, which means you're no longer putting calcium into the cytoplasm, which means you no longer have calcium down the troponin, which has moved tropomyosin out of the way. So the tropomyosin comes back, you close those binding sites, and the myosin comes off, no more muscle contraction. Okay. I believe this is, so our calcium. When the stimulus from the nerve stops, the calcium that is in the cytoplasm, in that muscle fiber, is going to diffuse out of the sarcoplasm and back into the sarcoplasmic reticulum. Now, it says diffuses, but we are actively pumping that calcium out of there. We want to get it out of the area as fast as we can. So we're going to pump the calcium back into the sarcoplasmic reticulum, where it will stay until we get another action potential. Okay? All right. The removal of the calcium causes the troponin and tropomyosin to return to their original shape and position, and we cover up those myosin binding sites. So now myosin can no longer bind to the actin. Okay, so this prevents the attachment of myosin, and the thin and thick fibers are no longer attached to each other. All right, really quickly, we've got like 2 minutes. Let's see if we can figure this out. With what you know about muscle contraction, the things that we talked about, look at this, talk to a buddy about it, and see what you can come up with. Well, why? Let's not try to, we'll get there, okay? Okay. So, does anybody know the name of this process? The stiffness of death. What's it called? Rigor mortis. So when you die, you get really stiff. Your muscles are contracted in whatever shape they were in before. Why do we not have relaxation of those muscles? So part of it is the ATP issue. Part of it is the ATP issue. Because what has to bind to myosin so that it will release from the actin? ATP. So ATP has to be present for the myosin to release from the actin. If you are dead, you are no longer making new ATP. Okay? So the heads don't detach. Second thing that's not happening goes back to the question you asked a second ago. If I'm contracted like this, what has to happen to make it loosen? If this muscle is contracted, I have to contract the other muscle to straighten it out. So we don't have those opposing muscles working to loosen it back up. Okay, so that's rigor mortis. But then if you let them sit for a while, so it says if the victim has been discovered 3 days later, you probably wouldn't have the difficulty because as you let them sit, they're going to start decomposing. And those proteins, those fibers, the myosin and the actin, are going to start being broken down. And when they start breaking down, you break those cross links, and then they're more flexible. So you can find death based on how stiff they are. Cool stuff. All right. Have a great fall break. I will see you guys on Monday.